Bismillahirrahmanirrahim. So students, we are dealing with the topic related to induction motors. And before we start doing this example, I would like to briefly shed some light over the basic principles of induction motors. So what happens is in this induction motor, we have a stator and we have three phase windings of the stator, and there is three phase electricity is connected, and inside the stator of the induction motor we have three phase winding which is in the spatial domain. So what happens is when we apply the power, three phase power, to the stator of induction motor, a rotating magnetic field is produced, and this rotating magnetic field is actually called a synchronous field, and the speed of this rotating magnetic field is given by the expression ns equals to 120 f over p, where f is the electrical frequency of the applied signal, p is the total number of poles inside the machine. Now this field, the rotating magnetic field, when we insert a rotor inside the stator of our induction motor, when this rotor is inserted, this synchronous field cuts the rotor and induces voltage in the rotor bars. This is actually winding of the rotor. This is cage type rotor, and as these windings are short circuited, so currents flow and the rotor starts rotating, trying to follow, because the rotor has its own magnetic field and it starts following the rotating magnetic field, the synchronous field, and it attains a speed. The speed of the rotor is called the mechanical speed of the machine. Now as this is the mechanical speed of the rotor. Now when they are rotating, there was this concept of slip, and there was a slip speed, which means that the rotor can never attain the speed of the synchronous field. It is always lagging, it is behind the rotating magnetic field, and that is why it is also known as asynchronous motor, not synchronous motor. And the slip speed, the concept of slip that was introduced, the slip speed is called, it is actually the difference between the synchronous speed minus the mechanical speed. Or we can also say that this was the slip speed. And a slip speed can also be calculated, and this was the slip speed, and then there is the phenomena how much slip exists. It can be calculated. The slip, which is usually denoted by S, is actually the ratio of n slip divided by synchronous speed, and it is usually in percentage. So by this formula we can calculate the slip S of a device, and this is a very important ratio which is repeatedly used in number of equations also. So by this equation we can calculate the formula for slip by using these three equations. The slip of a motor machine can be calculated. It is actually equals to n synchronous minus n mechanical divided by n synchronous into 100%. Or we can also calculate this if we want to calculate slip, we have mechanical and synchronous speed, and if we know the slip of a machine, we can calculate the mechanical speed by 1 minus s n synchronous. So this is how we can calculate the mechanical speed of the machine also. So this is a general overview of the few fundamental relationships that exist between the rotating magnetic field and the relationship between the mechanical speed and the concept of slip. Now let's look at the first question. It states that we have a three-phase for 60 volts, 100 horsepower, 60 hertz, 4 pole induction machine, and it's delivered rated output power. And there we have the slip, that is 0.05, or at times you will get slip equals to 5%. Both are the same. So the first part is determine the synchronous speed and the motor speed. The motor speed is actually the mechanical speed, and the synchronous speed is n synchronous, or we can denote it by ns. So for part A, we know that n synchronous equals to 120 F electrical over P. So Fe we have, it is 60 hertz. And how many pole? 4-pole machine. So the value of synchronous speed will become n synchronous equals to 1800 RPM. Now the second part was of part A was to calculate the mechanical speed. Now the formula for mechanical speed is 1 minus S divided into n synchronous. Slip we know, this is 0.05. Synchronous speed we have calculated 1800 RPM. So the mechanical speed of the machine will become 1710 RPM. What this means is that the rotating magnetic field, this is the synchronous field, and this red line, the rotating magnetic field is rotating at 1800 RPM, and the rotor is rotating at 1710 RPM, and there is a slip. Due to the slip between both of them, the speeds are not the same. Now the second part states that what is the frequency, speed of the rotating air gap field. So what is the speed of the rotating air gap field? Air gap means the air gap between the rotor and the poles of the stator. It is actually the synchronous speed. Synchronous speed is the speed of rotating field in the air gap, and that is actually 1800 RPM. So the part C is what is the frequency of the rotor circuit. So to calculate the frequency of the rotor circuit, there is a critical formula that was covered in the theory class also, but for the understanding I can say that when the slip is S slip is 1, that is maximum, which means that the rotor is not rotating, it is stationary, and the rotating magnetic field is rotating at its maximum. So that means the slip at that time, from this formula you can see that synchronous is maximum and mechanical is 0. So at that time slip is 1. And when the slip is 1, the rotor frequency, the frequency that is induced over the rotor, is actually equals to electrical frequency. Now when the slip is 0, that means rotor is rotating aligned with the synchronous rotating magnetic field, then there will be the rotor frequency will be 0. So this, from this relationship we can say that rotor the frequency that is induced on the rotor is actually equals to slip times the electrical frequency. So Fr, the frequency over the rotor, is equals to, that is why slip is a very important concept, and by this E is for the electrical frequency, or we can say that, and this will become 0.05 into electrical frequency was 60 hertz. So the frequency of rotor is 3 hertz. Now for the next part we have slip RPM. So by the same concept as I have explained you now, this is a very important concept that will keep on repeating the concept of slip. So slip RPM actually means, as I have shown you, slip equals to speed of slip is synchronous speed minus mechanical speed. And what we have, 1800 minus 1710, that is equals to, and slip is actually equals to 90 RPM. This is one concept. This is the one way we can calculate this, or we can also calculate this if you like to, that n slip equals to s into n synchronous, and this will also give you 90 RPM. Now the part E states that what is the speed of the rotor field, relative to the, now the rotor has its induced currents, and what is now the speed of this relative to different things. Number one, it says what will be the speed relative to the rotor structure. So for the rotor, the field that is being induced over the rotor by the synchronous field is there is a lag of because the rotor the mechanical speed is lower than the synchronous speed. So this will be actually, for the rotor structure, this would be 90 RPM. This is the actual speed that the rotor will be experiencing because it is slower than the synchronous field. So then for the stator structure, for the stator structure, that is the stationary body structure, it will be actually equals to 1800 RPM. And for the stator rotating field, it will be actually the stator rotating field, it will be 1800 RPM, and the stator structure, so this will be actually 0 RPM. The rotor field will be having the same field as that is of the synchronous rotating magnetic field. This field and the field that is cutting this are actually the same field we are talking about. And so the last part states that what is the rotor induced voltage at the operating speed. How much voltage is induced in the rotor when it is rotating at the operating speed, and there is this concept of a turns ratio. So this is a very important concept. The induction motors are also known as rotating transformers. So why they are known as rotating transformers? Because in a stationary transformer, we know that the primary field is producing a flux, and the winding is stationary, but the flux is changing and it is cutting this winding and it is inducing. The very important word is, in a stationary transformer, inducing a voltage. Now, if we closely look at our induction motor, here the scenario is also very similar. There is a flux, and there is the stator windings produce a flux, and this flux cuts the winding in the rotor and it induces voltage. So that is why the principle of induction, similar to transformers, also exists in induction motors. And so there is this concept, as you have studied, there is this concept of turns ratio also when we make an approximate equivalent circuit for our induction motor. So what it is asking you in this question is, E we have done, and in the part F what it is asking that so how much is the voltage that is being induced in the rotor, how much voltage is induced, let's call it ER, when it is rotating at the mechanical speed of 1710. So by the formula we know that the voltage induced in rotor has a direct relationship with the voltage that is applied multiplied by the slip. And E2, So we have this relationship, that is E R dash, and this E R dash is actually equals to S A effective, or the turns ratio multiplied by E R naught. And this E R naught is actually the at a zero speed, locked rotor speed. This will be actually equals to the phase voltage that is applied on the terminals of the machine. So so the voltage that is induced in the rotor is the slip. We know that it is 0.05, and the turns ratio they have given to us is 0.5, and our the voltage, that is ER naught. ER naught means when the rotor was locked and there was a synchronous field cutting this rotor, how much voltage was induced. So this voltage was actually the voltage that was induced at that time was actually equals to the what was the voltage being supplied. And for the per phase equivalent circuit, we have given it is a Y connected motor with a line to line voltage is given. So we convert this into phase voltage. So the rotor speed would become the induced voltage on the rotor will become 6.64 volts per phase. So this is the concept that explains that how much voltage is being induced in the rotor. This voltage is producing a specific current, and that current is producing a magnetic field inside the rotor, and that magnetic field that is produced in the rotor is trying to follow the rotating magnetic field in the stator, and the motor is rotating at 1710 rpm. That is how this motor is functioning. I hope it helps. Thank you.